RIC is a configurable real-time controller for the RAN. It allows RAN control functions such as handoff management, load balancing, and interference management to be implemented as microservices we call XApps. Low latency is crucial for such control functions. A 10 millisecond end-to-end latency from RAN to RIC and back means that the latency inside the RIC must be as low as 2 milliseconds. The RIC is built on a microservice architecture that allows XApps to be implemented by different companies using different programming languages and tools, providing the combination of predictable sub-2 millisecond latency with the flexibility of such microservice architectures is challenging. To meet these challenges, the platform provides policy-driven, low-latency messaging and in-memory databases built using open-source technologies. Other techniques, such as control loop-aware dynamic resource management, will also be explored. We demonstrate the platform capabilities using an inverted pendulum. Like the control of a RAN function, the control of the inverted pendulum is implemented as an XApp and requires low end-to-end control loop latency. The demo uses the same platform required in RAN control, including SCTP and ASN1 encoded messaging. Inside the RIC, the policy-driven messaging is used to route the messages. The RIC dashboard shows several graphs describing the current state of the RIC. The pendulum control loop latency is the time within the RIC to process a pendulum control message. The pendulum control load tracks the total number of pendulum control-related requests processed per second. The RIC total load shows all requests that the RIC is currently handling, including non-pendulum related messages. The goal of the RIC is to provide sub-10 millisecond latency. The inverted pendulum shown is representative of real-world industrial processes that also require low latency. The initial RIC latency shown in the graph is 2 milliseconds, and you can see that the pendulum is still stable. Now we will increase the latency to 8 milliseconds, and though it wavers briefly, the pendulum remains stable. If we increase the control loop latency to 15 milliseconds, which is more than our guaranteed RIC latency of 10 milliseconds, the pendulum becomes unstable and falls down. We will now simulate an increase in the total RIC load corresponding to the kinds of loads we expect to see in the field. As you can see, the RIC latency guarantees are met and the pendulum remains stable. This demo shows that the RIC can indeed meet the time requirements of pendulum control, even if background traffic is introduced. We've also demonstrated that if the RIC were slower, accomplished by introducing artificial delay, that pendulum control is lost.